Um, let me just check off a few more names. Oh, okay. I don't know that I have any announcements. The test 5, chapter 10 part is completed, or should have been. Your activity 7 is completed. It should have been. I have covered gas laws, a brief intro. My plan is today and Wednesday to answer any and all questions you might have with those practice problems. There have been three now that I've sent out with the answers. It's possible that I have an incorrect answer. So if you're doing these problems and you're not getting my answer, then maybe we should go over. I've got my answer keys by me, but there's one concept that I wanted to go over today, and then we'll start answering questions. I'm going to start with the summary. These, in chapter 11, I consolidated all of those gas laws, which are just simply formulas, into 6. They have names. I do not plan on asking you to name them. You don't have to name them on your final exam. But the reason why I'm writing some of their names here is in case you need more practice, you can go to the slides or to your textbook or any textbook and Google or whatever these names and then get some practice on them. Hold on, let me sorry, this person in. Oh, the reason why I started the class a little bit earlier today is because I definitely have to end by 9:30, and I figure you're going to have some questions, so I want to, make the most of it. So on Wednesday, I'm going to try to do the same thing, start at 8:30. My hope is to have the other part of test 5 made for you guys to take starting Friday. And go through Monday morning before class. So that's my hope. I'm going to work on it some, maybe this afternoon and tomorrow. Tomorrow is my lightest day of my week, in that I just have the one lecture. Okay, anyway, back to my formulas. PV equals nRT is the ideal gas law. It is the most popular one. Because you're using R and it's specified with that combo unit, you have to have pressure in ATM, you have to have volume in liters, N stands for moles, moles are moles. Temperature in any of these formulas must be in Kelvin. The combined gas law does not make use of R at all. So your pressure can be in any unit as long as it matches and cancels on either side. Your volume can be in any unit as long as it matches or cancels on either side. Your temperature must be in Kelvin. Let me let this person in. Okay. This is a shortcut from PV equals nRT to determine a gas density for any gas at STP. If those are the conditions we want you to determine the density, it's simply the molar mass of that gas divided by that magic 22.4. If your word problem says it's collected over water, measured over water, whatever, something water, you must correct. Now this T is, when a little t is by another variable, it stands for total. It does not stand for temperature. So this is your total barometric pressure equals your dry gas pressure, the gas you're collecting, and your water vapor pressure. A strong hint in the problem that you're using this is not only the phrase collected over water, but they give you the water vapor pressure. This is part of Dalton's law, and so is this one, where the A stands for one of the gases in the mixture, the T is the total pressure given, N is moles of A. This one's that particular gas. It's a direct relationship. And then if you have a mixture of 2, 3, 4 gases, yes, you're going to have to get A, B, C, D, different gas partial pressures, different moles, sum them up, and just do this formula based on, it's a direct relationship because P and N are on opposite sides of the equal sign. The last one down here is Graham's law. The lighter the gas in terms of molar mass, the faster it will move. Move meaning diffuse, effuse, it's a speed or rate. So this we've already covered. I just wanted to sum that up again. If you need me to pull that sheet back up at the end, I will. Hold on, let me get a couple of these names that came in. Okay. Now, the new additional last concept, and there's 3 main concepts that don't require laws. And one of them is, as you increase temperature on a gas, yes, the motion of the molecules will speed up. So your kinetic energy, kinetic means energy of motion, will speed up as temperature increases. So that's a concept. If you increase the pressure on a gas, if gas molecules, expand and occupy the space of a container, so there are no real attractive forces for gas molecules. But if you have, say, 2 gas molecules here and you sufficiently increase the pressure on them, if they get close enough, they can form a liquid. So increasing pressure will start to form the liquid, and you're less likely to have the gas state. If you decrease temperature, see, gas molecules like to move around, and as you increase temperature, they move around faster. If you decrease temperature, their motion gets so slow that they could attract to one another and then liquefy. So the 2 conditions that we can deviate from having the gas would be increasing the pressure or decreasing the temperature. Lastly, this is the last main concept, and it is a formula, but I'm going to try to teach it as a trick. Let's see, let's say I have this reaction. This is called methane, but what I've written here, gas, 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 it's combustion. So they're all gases at this temperature, very hot temperature here. So I have conditions here for my oxygen. I give you a pressure, I give you a temperature, I give you the volume. I simply want to know, well, what volume of CO2 can I collect at these same conditions? Now, because I'm comparing a gas to a gas, and we know this law down here, PV equals nRT, volume is directly related to moles. See, I've got it here. Volume is directly related to moles. So if I'm not changing the conditions, see, I'm keeping the conditions the same. Look what you can do. You can say volume of the O2, simply use your mole ratio, and get the answer. No plugging in needed at all. Now, to prove this, watch what I've done. Let's see. Okay, same reaction. Ideal gas law. Rearranged it to solve for moles. My pressure's in ATM. I did need to convert my volume to liters. I did need to convert my temperature to Kelvin. When I plug in these conditions into this formula, and also notice I have to know R, I get that number. That's oxygen's moles. So watch what I'm going to do now. I simply use my mole number, mole ratio, moles of CO2. I plug back into PV equals nRT, same conditions, and like magic, I get the volume again, the same one. So you have a choice, guys. You can do it. This is called the long way, or you can now know, hey, if you're comparing two gases at similar conditions, just use the mole ratio on your volume. Questions? You can only do that if you're comparing two gases. I'm going to do another example because I want to make sure y'all know this.
I got a quick question that's not related to this exactly. It's about the Q.
I'm sorry, it's about the Q?
Sorry, my mic. It's about the Chem 101 thing that was due yesterday.
Yeah.
So one of the questions said that there was a reaction of A yields B, and then like a total change of heat of negative 10 kilojoules per mole. And it said, right, what is missing from this? And I didn't know what it was asking for.
I'll have to go back and look at the question, but if it's A goes to B and there's a negative number, that means that that particular thing is exothermic. Now, if in your overall, did it give you a goal reaction?
No, that's all it said was like A yields B, and then it gave me a negative 10 kilojoules per mole, and it said which number is missing from this reaction. I kind of just guessed, but like I wasn't, I didn't know exactly what it was asking.
Okay, I'm gonna make a note, and I'll go back, and then I'll email the class.
So, yeah, me too. I got the same problem with that question. I was lost. I was like, I don't know what they asked me. I don't know.
Okay, so it says A yields B, and then it gives you a negative kilojoule number.
And then
yeah,
it goes
negative 10.
B to C.
I'm sorry, what?
It's fine. It goes B to C.
Okay, so A yields B, and then it said B yields C.
Yield C.
Oh, and
it
want you to go to A
five.
to C?
I
Yes.
actually think that it was A to C and then B to C.
No, it's A to B, negative 10. Then
Okay.
it was B
My bad,
to C is 5. And then the last one was A to C with a blank. And we need to fill the blank in.
Oh, yeah.
Oh my gosh, guys. Yeah. So your B's cancel, and the answer is negative 5.
That's what I put.
I got it anyway. Yeah.
Oh my gosh, guys. I now remember when I selected it, I thought, oh, this is a gimme, an easy one. Okay.
I must have not seen the whole thing.
The gimme ones are usually the ones that cause us to overthink.
Because I said it to myself that was it's so easy. I feel like she was trying to trick us, but I was like,
No, I was trying to be nice. I'm trying so hard, guys, to be nice.
I have a question related to the paper.
Okay.
Can you put the paper that said take the gas and do the mole ratio? That one.
Okay. Is it
If
this
the
one?
goal was to Was that the one?
Well,
Yeah,
here,
that was it. That was
is
it.
it? Okay.
The goal was to
Before you-
find the moles, right?
No, that's
Never
not even
mind,
needed.
find
That was my
volume.
point. That was my point.
Oh, okay. Okay. I was confused because we found the volume and I was like, wait, we were trying to find the moles, weren't we? Okay. That's
Oh,
my
no,
bad.
here,
Yeah.
look, hold on, here. If I give you these conditions, and there's a volume here of 250 milliliters,
Mhm.
and I'm simply wanting to know, hey, well, what volume of this gas can we make at the same conditions?
Yeah.
Then you take your given volume times your mole rate, or your mole ratio, and you get your answer. Why can we do that? I didn't change the conditions, so the V is in, right? It's directly
Right.
related.
Okay.
Does that make sense?
It makes total sense. I confused
now-
myself on a different matter. We're good to go.
Okay, well, wait, let me just say something. Okay.
Okay.
Let's say, same question. I give you these conditions, right? Now, listen, hear me out. I want you to do a volume, but Morris here changes these conditions. Guess what you have to do?
If the conditions are changed.
Yeah. You have to do, well, hold on. You have to do, let's see, where is it? PV equals nRT twice. You have to do it to get the moles of the oxygen. Then you have to do it again using PV equals nRT, but now the conditions have changed, right?
Yeah.
Are y'all following what I'm trying to say?
I do.
Yes or no? Yes or no?
Yes.
Okay.
Yes.
Okay. Now, this is reminding me of something. And this, we're branching in different directions, but hold on. Abodi Katham. Your name on my roll is Abdullah Hamdan. I'm only
Yes.
mentioning, I'm mentioning if your name does not match your P number, when you go to take that final exam, you're not going to be able to take it.
Oh my God. Okay. I will try today.
Because
Put my
Malaz,
participate.
Malaz, I'm sorry if I'm not saying your name right. You've changed it back to the right name. I'm meaning the name that I have on my roll.
Yes, I did. I did that by
Thank
for the participant button here. So
Thank you.
after you log
Because if you did not, you would not be able to take the final exam. I'm just
Oh,
mentioning that.
it's good you tell me that. Okay.
Yeah. Okay. Now, where was I? Okay.
I tried
And
to change the
when
name
you will,
a new account, Zoom account, but with my philosophy email account, but it still get me that name again. So I tried, but I don't know how to fix.
You need to, both of you need to call help desk, I guess, or email and say what I just told you. Does that make sense? Maybe write both of your, the names that sometimes that appear, and say that I'm afraid that my chemistry professor said I might not be allowed to take the final exam if the name is different than the name given on D2L. Does that make sense what I'm trying to say?
Yes, sure.
Okay, I just, when I saw these names, I thought, well, I better make that announcement.
Thank you so much.
You're welcome.
the final will be on D2L or on Kim or
D2L, it's a proctored exam. It's going to be on D2L, and I will give y'all instructions as soon as I'm told what they are. You'll probably, now don't quote me on this, you'll probably have to go to your chemistry 1110, this is D2L now, chemistry 1110, all labs or the merged labs, and then find it there. But it's not there yet. So let's just get through this week. And then
Like,
we'll
can
worry
you
about
send
it
us
next
the
week.
practice? Can you
Can
send
I
us?
send out? Yes, the final exam practice.
Yeah, soon, just soon.
Yes, I will send out the 11-10 final exam. I'll send out both the student copy and then the one with answers. And y'all can just have fun. Okay, you can have fun with it.
Yes.
Okay, now let me take a breath. Questions now. I've given 3 practices. One was called, where are they? Sorry. One's called practice number 1. These are gas laws, chapter 11. One's called practice number 2. And the last one was an old test from last summer. But if you look at them, they all have similar wording of questions or problems. So I'm not sure, Eric, if it was you or somebody at the very beginning said, hey, or can we go over some of the practice? Here's your chance now.
2 on practice 1. That
Okay,
was yeah.
Okay, which one?
It said practice number 1. That's SP 20 Chem 1110 chapter 11 practice 1.
Right. Okay. Which problem?
Number 2.
Okay, the second one. Okie dokie. Do I need to hold on? Hold on. Let's see, which one is it? Can y'all see? Can y'all see this problem?
Yeah.
Yeah.
Okay. How about let me read the problem out and go over the hints, and then I'll sort of set it up on another piece of paper. Is that good? Okay, here we go. It's basically saying what volume of oxygen collected over water. Okay, automatically I see that collected over water, and you see this little this formula right here. I'm going to have to put 748.5 as total pressure. I'm going to solve for my pressure of oxygen, and I know my water vapor pressure. It's right here, VP, water vapor pressure. This number here is 22.38. So when on my paper, when I subtracted that out, I got 726.1. Now, in a minute, I'll put it up on another piece of paper. I'm just saying that's what I had to do first. I see this temperature at 24.0 degrees Celsius. I had to convert it to Kelvin. When I converted it to Kelvin, I got 297.2. Okay, so my hints were go ahead and correct the pressure, convert your temperature to Kelvin. Now you have to write the reaction, the balanced reaction for gold 3 oxide, arrow with heat, gives you just gold metal plus O2. O2 is the gas. You've got to balance it, convert this mass here to moles, and then use your mole ratio to get to oxygen. Okay, are we ready for me to set up the problem now? Because I'm gonna have to stop share.
Yes, ma'am.
Sure.
Okay, here we go. So I'm going to write my reaction. Let me go ahead and write the numbers too. What I'm getting ready to show you guys is the common misstep. Okay, can y'all see my paper? I had to write my reaction. This given 4.420 grams, gold 3 oxide is not a gas. Yes, I had to convert it to moles to use my mole ratio to get to my gas. This is the N I put in my formula. So if you've corrected your pressure and you've got to change it to let me go ahead and do that. So my pressure number and I'm going to go ahead, since I'm writing it out, I'm going to write my temperature one too. Okay. I corrected my temperature up here. I took my total pressure minus my water vapor pressure. That's still in millimeters of mercury, so I had to convert it to ATM. I know my N. So the last step is plugging in to PV equals nRT and solving for volume. So I corrected my pressure. Here it is. I don't know my volume. My moles was on that other sheet of paper, 0.01500 moles of oxygen. R is a constant. Temperature, I converted up here. Eric, did I set this up sufficiently now for you?
So yeah, so I guess in my notes, I guess I just missed writing down a step. You have to, when you're using PV equals nRT, you have to use atmospheres.
Yes, because the R.
Okay, so that was my mistake, because I didn't convert that, so
Right.
I'll write that back in there.
Okay.
Thank you very
Next.
much for going over that.
So now, see, now on the other two practices, I've given similar. So now you can practice it 2 more times.
Okay, I got it. Everything else was good for me there. I just
Okay.
missed that one. So thank you.
I had a question for you about the first one. I don't know what formula to use for it. Or is it because I'm overthinking it? Then it's simpler than nothing.
The gas density of sulfur trioxide?
Yeah.
Okay, hold on. Where my finger is. Any gas density at STP is the molar mass of sulfur, on this one, sulfur trioxide, divided by 22.4. That's the formula you use. And then if we want the volume and we give you a mass, you're just using your density is mass over volume formula. Manipulate that. Now volume is mass over density, and you solve.
Oh, okay. Because I think I used the first formula you just showed us, and then
Here. It's right here. It was 2 parts. Part number 1 was a gas formula. Part number 2 was a chapter 1 formula.
okay. Thank you.
Okay, next question. I would do these practices in order of number 1, then number 2, then number 3. Because number 1 had hints. Number 2, same format, but no hints, no formulas. So I'm asking you to practice deciphering the word problem, like which law am I going to use? And then number 3 was an old test from last summer. Now, the test that I'm going to create on Chem 101 will be some multiple choice, okay? And then some where I'm going to create the problems like these, and you're just going to have to write the answer in. That's why I gave 3 of these practices.
And
That's
when
why
is
Go
Chem
ahead.
101 test gonna be?
When will this test be?
Yeah, the Chem 101 that you just said.
I'm going to start it Friday morning, and it's going to go through Monday, like at noon. And it'll be it's worth, the 80 points because y'all have already you took the chapter 10 part.
So can you just kind of go over what like the rest of our semester looks like?
Sure. This week is answering questions, like this Monday, Wednesday, answering questions on gas laws. Friday, I may start the non-math part of the last chapter, which it'll take me not even 20 minutes to do it. But when I do it, when I do my lecture notes and when I go over it, I'm probably going to say, you need to know this for your final. You need to know this for your final. And then Monday of next week, I will finish. There's another, I'm sorry guys, a calorimetry problem that's introduced in chapter 12 involving phase changes. So I have to introduce, that's math, but I'm going to try to wait to do the math till after you test on the gas law math. And then Wednesday and Friday of next week will simply be, I hope, just review or, answer questions, or you can ask me questions on that practice lecture final that I'm going to send you today. And then that next week is the final. It's 50 multiple choice questions. It's been a long time since I've looked at it, but I'll try to look at it and tell you, okay, there's 14 calculator problems. The rest are like, name this or what's the oxidation number of that. I mean, I'll try to break it down for you.
Is there a time frame that we'll have? Not like during the test, but that week. Are we gonna be able to take it?
I don't know.
Okay.
I don't know that yet. I know that it's a time limit of 1 hour and 50 minutes. I do know that. So once you start taking it, you have 1 hour and 50 minutes. Most students finish it in a little over 1 hour. So, I mean, I'm just saying that maybe, I don't know that you need to rush. I think you're going to have plenty of time to do it. Okay, so another question. I mean, we still got like 25 minutes, guys. I could go over this is a chapter 12 thing, but it's an easy thing. It's a picture. I can draw a picture and label what the picture stands for, because that's one of the questions on your final exam. But I thought that maybe if y'all had tried at least the first practice, y'all would have questions with gas laws. Oh, wait, that's what I was going to do. This is gas laws. Okay, let's see if we were listening at the beginning of today. Now, let's see. Let's say I give you this reaction. Nitrogen reacts with hydrogen and makes ammonia. These are gases. If I say you have 6 liters of hydrogen at STP, and I simply want to know the volume here of ammonia at STP, how would you do the problem? What would you have to do very first? Anybody?
First, you would need to balance the equation.
Thank you. Okay. There we go. What would you do next?
So you know volume is additive, so we have to figure out what the nitrogen is.
I think we just use the mole ratio, don't we?
Yes. Who was that? Yes. So what's the answer here?
What's the answer there? Is it 4?
Yes, it is. Okay. That's how you do it. No, wait. Let's write it out. Well, somebody was listening. This is how you do the problem, guys. Now, another one. And I'm going to purposely do a reaction. Y'all have done, well, you did it one time in lab, and then you watched me do it for the oxygen lab. Okay. What would you have to do first? See, what I'm saying is I have some magnesium, I'm reacting it with oxygen, and I'm making magnesium oxide. If I know I have 10 liters of this oxygen at STP, I want to know the volume over here. What would you have to do first?
Ounce.
Okay. Can somebody tell me what the answer is?
20.
No.
5.
Uh-oh.
Oh.
Let's analyze it. Let's look at
Got
it.
him. Did you expect someone to say 20?
Oh, that's so.
Oh, okay, maybe.
What would it be here?
Is it 10? Because O2? Okay, no, I'll stop.
Okay. Morris is trying to be tricky, but it's the concept. Is magnesium or magnesium oxide, are they gases?
No, they are not.
You can't do gas laws on solids. So you would put cannot determine using a gas law. And where is this coming from? On practice number 2 of the gas laws, I asked that kind of question. You can only do my trick of a volume with a mole ratio to a volume if you're comparing 2 gases. Could y'all follow that?
Yes, ma'am.
Yes.
Okay, well, now we won't make that mistake. Okay, another question. I just thought I would do that concept because you'll see it. I've asked it, the ammonia one I asked on your practice number 1, and then on practice number 2, I think maybe it's still ammonia, I don't know. Yep, it's still ammonia, but on that test practice for the summer, it's a different reaction. Now, let me ask the class this. Let's say I give you, okay, here's one. Gosh, I'm really going through paper today. It's okay. Let me write the reaction down. Okay. This is ethanol. That's ethyl alcohol. This is oxygen. This is carbon dioxide. This is water. Why do you think in a problem we would report this temperature like this versus, say, room temperature? Anybody want to give me
Because it's a combustion equation.
And if I give you a hot, hot, hot temperature, what physical states are these now?
Gases.
Exactly. So if I give you a volume here at this temperature, and I want to know a volume of steam at that temperature, once the student balances, and I give you this volume, you can use your mole ratio. Are y'all following what I'm saying?
Yes.
Yeah.
Perfect. So my point there is, if you see a reaction and then, you know, oh gosh, why is she giving us this hot temperature? I'm trying to say they're all gases. Because ethanol, ethyl alcohol at room temperature is a liquid. Water at room temperature is a liquid. I'm just saying. Okay, another question. Anybody? Or do you want me to do my phase diagram picture?
This is another random question,
Okay.
but I thought that like with combustion, one of the big things, you know, like in your car exhaust, I don't know if it's the same, but you know, you're always worried about carbon monoxide.
That's not with gasoline does not completely combust. It produces the lower oxidation state of carbon oxide, yes.
Okay.
If you had a clean combustion, then it would be producing CO2. Did that answer your question?
Yeah.
Yeah. And gasoline's a mixture of a lot of different organic stuff. So it doesn't have a clean combustion. A clean combustion would be CO2 and H2O.
Okay, thanks.
Mm-hmm. Let's see.
Can you go over the three concepts?
The
There were
what
three concepts that you mentioned.
The
molecules and
Yeah.
like one of them is when it speeds up, it can go to a liquid.
Yeah. Hold on one second. I'm just trying to figure out why. Oh, here it is. I was off by one person. Okay, sorry. Okay. Goodness, why is she? Hold on. I have an 11:20 person coming in crashing this 11:10 lecture, which is fine.
You probably might have entered a wrong code in there.
Uh-oh, did I send the wrong code?
Let me go ahead and check.
Sophia? Did I send, Felicia, did I send the wrong code? Okay, I'm sorry.
So, yeah, you sent the same codes for both of our meetings.
Okay, when I'm going to get out of this meeting here in like 10 minutes, and then I'll go back and send the other code. I probably just, yeah, my mistake. Yeah, it's bound to happen. Okay.
Edward. Oh, sorry.
What?
Oh no, I was telling something to my brother.
Okay. Here are, was it Devin who asked? Anyway, here are the three
Yes, ma'am.
concepts. When gas molecules do not have attractive forces, so they're moving around, and if they're in, say I have not a liquid but a gas in here, and I open the top, those gas molecules would occupy, if I close the door to this room, they'd occupy the space of this room because there's nothing really holding them together. Now, the motion of those gas molecules, they're in constant motion. They move. If I increase temperature on a gas, they move faster. Okay, so that's concept number one. Concept number two, and that famous law, PV equals nRT, if you look at just pressure, what could you do to pressure so that you don't have a gas anymore? If you increase the pressure on a gas, you're forcing those molecules to be really close for an extended period of time. They will create an attraction to one another and form a liquid. So increasing pressure on a gas, you're less likely to have a gas. If you decrease temperature on a gas, if you cool it down, the molecule speed goes really slow. They can then interact and form a liquid. And that's what we're going to show in chapter 12 with the phase diagram. So that's a concept. And the last concept was basically, was what I did at the beginning. Let me get my other. Okay, I'll do it this way. When you have you're comparing two gases at similar conditions, you can use a mole ratio on it. But if you're comparing a gas with a solid, you may not do the mole ratio trick because you can only use the volumes directly related to moles for gases only. Did that answer your question?
Absolutely. Thank you.
Okay, those are the three main concepts. Sophia, are you in this meeting?
I think she left.
Okay, yeah, we're gonna end this meeting soon because I screwed up and sent my 11:20 the wrong the wrong time. Okay. Anybody have another question or a problem type on gas laws you want me to go over? To make it worthwhile for Wednesday, at a minimum, 2 out of 3 of those practices need to be attempted. Best case scenario is all 3. You'll see a pattern with them. Anybody else have a question? Oh, the reason why, for those that came in after, I started the meeting at 8:30, and I'm going to go ahead and start the one on Wednesday at 8:30, just so that we have more time for more questions. I know the class time doesn't really start till 8:35, but I just was afraid that y'all would have more questions, and I wanted to cover at least an hour's worth of stuff. But it looks like, I'm just guessing, it looks like maybe we haven't done the practices yet, except for maybe a couple people. So are we good for today?
Yes.
I would say so.
Yeah, I think we're good. On Wednesday, I will have more questions.
Okay, good. Yeah, what I'll do is I'll look at the 3 practices because I can anticipate the ones y'all are going to ask me. So I'll go ahead and have those written out. I mean, I've got my keys. They're all written out. I had to work them just so I could make sure I had the answers to send y'all, the numerical answer. Okay, Felicia, you may stop the recording.
Okay.
And thank you.